Right, today you're going to be working on learning target 2, which is explaining how the concentration of hydronium ions affects the pH. And you are going to be practicing going from hydronium ion concentration to pH and from hydronium ion concentration to hydroxide ion concentration. The hardest part for a lot of this will be entering the numbers on the calculator for a lot of you because it's something you haven't done before. Well, you should have done it yesterday with logs, but it might take a little bit getting used to. So I highly suggest you use your regular calculator, not your phone. The calculator you will be using on the test so you get used to how it works and you're not trying to learn a new calculator the day of the test. A couple of things we have to understand, and some of this was in the POGL from yesterday, so you can maybe kind of go through some of this a little faster or skip it if you think it makes sense. But water is something that's called amphoteric. It acts both like an acid and a base. So in this equation we have on this slide here, we can have the hydrogen from one water going to the other water to make a hydronium ion and a hydroxide ion. In pure water, the amount that this happens is always the same, so that you'll always get 1 times 10 to the negative 7th molar hydronium ion. That should have a unit on it, and the same concentration of hydroxide ions. So you get the same hydroxide and same hydronium ion. So water is overall neutral because you have just as much hydronium as you have a hydroxide. If you multiply the hydronium ion and the hydroxide ion, that's hydronium ion, that's hydroxide ion. If you multiply the concentration of hydronium ion times the concentration of the hydroxide ion, you will always get the same number. So this is called the ionization constant of water. And anytime you take the hydronium ion times the hydroxide ion, no matter what the solution is, you'll always get the exact same number, 1 times 10 to the negative 14th. So that will allow us to go from either hydronium ion to hydroxide ion or from hydroxide ion to hydronium ion. So you can find one if you know the other. If you add acid to water, it's going to increase the hydronium ion and it will decrease the hydroxide ion, and adding base to water will decrease the hydronium ion and increase, this should be increase, the hydroxide ion. However, that product, like I mentioned before, is always going to be 1 times 10 to the negative 14th. So in an acid, the hydronium ion will be bigger, and in a base, the hydroxide ion will be bigger. But you multiply those two numbers together for any solution, you're always going to get 1 times 10 to the negative 14th. Now, from the last two problems, you saw that we're dealing with a lot of scientific notation. So this is why they developed the pH scale. So if we look here, a pH of 0 has a hydronium ion or hydrogen ion. These two things are kind of always going to be the same number, of 1, and that has a hydroxide ion concentration of 1 times 10 to the negative 14. So for the most case, if you look at all of these numbers, we're dealing with some really small numbers that are going to be cumbersome to write. Sometimes it's not bad, like having a hydronium ion or hydroxide ion concentration of 1 isn't bad. Then on the flip side, to have a hydroxide ion concentration of 1 times 10 to the 14th, those are cumbersome to write all the time. So this is why they developed the pH scale. So the pH scale is a base 10 scale. So every increase in pH, so as we go from a pH to 1, from 0 to 1 or 1 to 2, we're changing by a factor of 10. So from before, we know that the lower the pH, the stronger the acid. So if we were to go from a pH of 4 to 3, the hydrogen ion or hydronium ion concentration is going to be 10 times bigger for a pH of 3 than a pH of 4. So it's a base 10 scale. So every increase changes by a factor of 10 because we're dealing with such small numbers like 10 to the negative 14th or 10 to the negative 9th. Those are going to be really not easy to deal with. So the pH is just an easier way of expressing how strong an acid is. So what you might be asked to do on your homework is a problem like this. It says determine the hydroxide ion concentration. And remember, another way to write that hydroxide ion concentration, just put hydroxide in brackets. And so you can write this way, so you'll often see it written that way. If the hydronium ion concentration, so hydronium ion concentration can be written with the hydronium ion, H30 plus in square brackets, is 0.45 molar. So if I know one, I can always find the other, because what we had on the last slide is the hydronium ion concentration times the hydroxide ion concentration always equals 1 times 10 to the negative 14th. So here I know the hydronium ion concentration, so I'm going to plug that in for the H30 plus. So then I get 0.45 times my hydroxide ion concentration, which I don't know, equals 1 times 10 to the negative 14th. So then I divide both sides by the 0.45. It's going to cancel the 0.45 out there. So I get the hydroxide ion concentration is equal to 1 times 10 to the negative 14th over 0.45. Be careful when you enter all these scientific numbers into your calculator. The warm-up, if you're having trouble, go back and watch how I entered those so you can see how to do it. So I'm going to enter the 1 times 10 to the negative 14th, divide it by 0.45, and I will get 2.2 times 10 to the negative 14th for that. So to calculate your pH, you're going to use the negative log. It's a way of undoing exponents. So to undo a multiplication, you divide. To undo addition, you subtract. Here we want to undo an exponent. So we want to undo this scientific notation with this 10 to the negative 3. And we're going to use the negative log button to do that. So for this first one, it's what is the hydronium ion concentration, or the hydronium ion concentration is 1 times 10 to the negative 3. So what I would enter into my calculator is what's the negative log of 1 times 10 to the negative 3. I could really get rid of the 1 there. And when I put that in my calculator, I'm going to get 3. It's whatever that exponent is without the negative in front of it. This one, negative log of 1 times 10 to the negative 9th, should give me 9. So these are easy because my number before my times 10 to the negative 9th is 1. It's going to be whatever my exponent is, but try putting these in your calculator when they're not hard. So when we get ones where you have to use a calculator, you know you are working your calculator right. So 1 times 10 to the negative 12 should give me 12 for a pH. So this is the pH of the first one, the pH of the second one, and the pH of the third one. So on this problem, it says determine the hydronium ion concentration. So that, if I'm going to write that in brackets, it's going to be H30 plus if I have a 0.25 molar solution of NaOH. So this is something that's a little different. NaOH, we learned last unit, this is a ionic compound because it's a metal with a polyatomic ion. This is, when it's put into water, it's going to split up into sodium ions plus hydroxide ions. If this NaOH is 0.25 moles per liter, I'm going to have 0.25 moles per liter of sodium ions, and I'm also going to have 0.25 moles per liter of hydroxide ions. So my hydroxide ion concentration will be equal to my hydronium ion, or to my concentration of sodium hydroxide. So if you are given the concentration of either the base, which is NaOH, or an acid, you can assume for this that the concentration of the base will be the concentration of the hydronium ion. So since this is NaOH, I'm going to get 0.25 moles per liter of hydronium. So of hydroxide. So I know my hydroxide ion concentration is 0.25. So then I will use that same equation we used on the last one, that hydronium ion times the hydroxide ion equals 1 times 10 to the negative 14th. So I now know my hydroxide ion concentration is 0.25. So I'm going to put that in for that. H30 plus times 0.25 moles per liter equals 1 times 10 to the negative 14th. Do the algebra, divide both sides by 0.25. So then I'll put, this is going to cancel out, I'll put the 1 1 times 10 to the negative 14th divided by 0.25, and I get 4 times 10 to the negative 14th molar. So now these problems you're going to have to put into your calculator. So when I do this, what I'm going to enter in for this problem to figure out the pH, I'm going to put in that it's the negative log of 2.4 times 10 to the negative 5th. I'm going to put that into my calculator. Negative log, and then on my calculator, parentheses already come up, so I'm going to do 2.4 times 10 to the negative 5th, and I get 4.6 is my pH. Now, I should be able to estimate that this is about 5, like this is 5, so I should be around 5, maybe give or take a little bit. That's your exponent. So if this was a 1, it would be a pH of 5. It's a 2.4, so it's a little bit bigger than 1 times 10 to the negative 5th, or a little bit less, so it's my 4.6. So then this one, I'm going to enter in the negative log, in parentheses 6.2 times 10 to the negative 3rd. So negative log 6.2 times 10 to the negative 3rd will give me 2.2 for a pH. And there is no unit on pH, so the pH is 2.2, no unit. Now this problem is a little bit careful. You got to be careful on what you're given. This is the hydroxide ion concentration. So in order to do the pH, I need to know the hydronium ion concentration. But I can use what we did on the previous slide and or previous section, and we know that the hydronium ion concentration times the hydroxide ion concentration equals 1 times 10 to the negative 14th. So I know my hydroxide ion concentration, so I can put this in for my hydroxide ion concentration. So I'm going to get the hydronium ion concentration, and then I'm not going to enter it into the math because this is going to be annoying with the scientific notation. I'm hoping you can follow. I'm going to do the 1 times 10 to the negative 14th divided by 3.5 times 10 to the negative 3rd. So I'll put that in my calculator carefully, making sure I use parentheses or my exponent button. 1 times 10 to the negative 14th divided by 3.5 times 10 to the negative 3rd gives me a hydronium ion concentration of 2.86 times 10 to the negative 12th. So then what I will do is find the pH by doing the negative log of that answer I just got, the 2.86 times 10 to the negative 12th. So negative log of my answer gives me a pH of 11.5, which my exponent's around negative 12, so I should expect my pH to be around 12, which it is. So that's my answer. So now in the next section, we're going to be going backwards. On this problem, we're going from the from the pH to the hydronium ion concentration. So if you know the pH, you should be able to find the concentration of hydronium or hydroxide ions, because we're just going to go backwards. So we're going to say the 10 to that exponent, the negative exponent. So pH of 6 is going to be 1 times 10 to the negative 6th. pH of 2 is going to be 1 times 10 to the negative 2nd. I'm just going to put my pH in for my exponent. A pH of 3 is going to be 1 times 10 to the negative 3. Now I technically don't need to put the 1 there, but typically it is, so I'm going to do it. And when we have pHs that are not whole numbers, that number before the times 10 to the negative whatever isn't going to be 1. So I'm just going to do that so it's consistent. So this is my hydronium ion concentration for each of those pH numbers. You just take whatever the pH is. If it's a whole number, it just becomes the exponent, and it's 1 times 10 to the negative 6th. So now these pHs aren't whole numbers, so you'll have to enter these into your calculator to get the right answer. So remember to find the hydronium ion concentration. We're going to do 10 to the power of the negative pH. So for this one, I will enter 10 to the power of negative 5.6. So on your calculator, the 10 to the power button, you can use a caret and stuff, but there's a button right at, like if you do second and look above your log key, there should be a 10 to the X. So hit that, and then you can put in negative 5.6. And this is not giving it to me in scientific notation. So what I'm getting on my calculator, and you can leave it this way, I'm giving 0.00000, I think there's 5 zeros in there, 2512. If you have a graphing calculator, I'm pretty sure it will probably go to scientific notation. You get 1, 2, 3, 4, 5, 6 spots I'm moving my decimal over. So 2.5 I'll round it to, times 10 to the negative 6th. And it's hydronium ion concentration. This has a unit of moles per liter, or molar. So 2.5 times 10 to the negative 6 molar hydronium ion concentration. And then this one, my hydronium ion concentration, is going to be 10 to the power of negative 9.2. So I will do second, and then the 10 to the negative 9.2. Put an extra key in there. This is giving me a concentration of 6.3 times 10 to the negative 10th molar. And pH of 1.34. My hydronium ion concentration then is going to be 10 to the negative 1.34. And if I put that in my calculator, forgot the negative button. It was way too big. I get 0.046 molar for that one. So not difficult, you're just using some different math than you've used. It's not multiplying and dividing, we're just using a different type of math. So then for our last example, this one says determine the hydroxide ion concentration of the following. So what equation we have is we know that the hydronium ion concentration is 10 to the negative pH. So I can find my hydronium ion concentration because I know the pH. So I can use the hydronium ion concentration is 10 to the negative 3.4. So I'm going to enter that in my calculator. Second, 10 to the negative 3.4. I get 0.0000398 molar. Then, using the equation we had earlier, hydronium ion concentration times the hydroxide ion concentration is equal to 1 times 10 to the negative 14th. So I want to know the hydroxide ion concentration. So I'll take 1 times 10 to the negative 14th, divide it by my hydronium ion concentration, which I just found, 0.0000398. Put that in my calculator, being careful of parentheses. Make sure I get the number of zeros. And I'm getting an answer of 0.25, I will round it to, times 10 to the negative 11th. And it's a concentration, so it's molar. So then for the rest of the hour, work on worksheet 3. The packet didn't get numbered, so be careful. Worksheet 3 has 2 sides to it. Both worksheet 3 and worksheet 2 should be done for Monday to check. You will have more time tomorrow if you don't finish, but I am going to have one more thing for you to do tomorrow, practicing with some titration work that we're going to start next week. And we only have 3 more weeks, like 3 weeks from today is the last day of the year. So double checked that you have all your missing work in. Think about if you need to retake a test, make some plans maybe for next week to get that done.